Hey everyone, are you able to hear me? I'm using some new software and I've got no idea whether the microphone on this is working or not. Tell me in the comments if you can hear me or not. There's also a little bit of a lag on YouTube, so I'm saying hello on here, but then I'm not actually seeing that on YouTube yet. Here you go, hopefully you see it now. Oh, I look a bit distorted on YouTube, I think. Awesome. Thank you, Daniel. It's weird, I can't hear myself even if I unmute myself back on here. Good. Am I also weirdly like distorted shape-wise? Let me just put a different screen up. Nice. Thanks, Nobs. Right, I've just put some Chrome on the screen. Tell me if this looks distorted as well. Sounds not very loud to you. Okay. That might be because you need to turn your audio up. I'm joking. I think it will have to be okay. I'll move the mic slightly closer to me. See if that helps. Yeah, I'm using a new setup. So I'm using Streamlabs, which is like an OBS version. Does that look distorted or does that look all right to you all? Yeah, I'm a little wide. What I'm more worried about is whether like the text and stuff is also going to be a little wide. There's a weird lag of about a minute between what I'm recording and not, I think. Here we go. Let me see if that's wide. We can also work out what the font size is that we need in order to be able to actually see this. Can everyone else barely hear me, or is it just Bobber Hop that's struggling to hear me? Have you got the actual YouTube video turned up on Max Bobber Hop? Very quiet. How do I deal with that? Okay. I don't think I'm going to be able to do much about the volume. Okay. Is that screen readable for you as well? Final question. Okay, everyone looks happy. Everyone's good. Let's. Okay. How big do we need this before you can read it? Okay. Thank you, everyone. Okay, so let's. Let me boost the text resolution. How's that? Can I stream any higher res, I wonder? Is it the resolution or the size that's not great for you? Okay, that works for you. Okay. Let's see if I can just. I'm just going to up my output resolution a bit. Okay, and we're just going to have to go with what we've got, I think. Otherwise, I'll spend the rest of the day doing this, but maybe we have another session afterwards and we can get this setup working really well. So, firstly, thanks everyone for being here. Hello, this is the official start. I'll probably crop all of that bit off. I thought it would be good to take a walk through the tooling infrastructure in Exercism. We have lots of different bits of tooling that run, test runners, representers, analyzers. They're built by lots of people, but I pretty much manage all of the actual software that runs it and architects it. And I think it's just useful and interesting to share that with everyone else, give everyone an opportunity to see how it works. And also lots of you will be software developers who have done similar things and will have lots of your own ideas on what we could be doing better as well. So that's sort of the aim of this session. I've got, as you know, if you've been watching this, YouTube comments open on the side. I would love to be guided by you. It's really difficult for me to know how to pitch this, at what level. Like, there's a lot of infrastructure, there's a lot of code, there's lots and lots and lots and lots of different moving bits. So what I really want is just to make sure that everyone that's watching gets a bit of a feel for what's going on, and that if you've got any questions or any bits you're intrigued about, that you get those answered. So please, just fire questions into the YouTube channel, and I'll keep checking that and answering as many as I can. Okay, so I'm going to start off at a really high level and then work down into detail. That's sort of the rough plan I have for this. So this, boost the font size. This is a test run in Exercism's editor. This is some brilliant dodgy data I've got. You can see there's both Tufa and lasagna, but you can ignore the dodgy data on my local machine. But I just want to show you locally as a starting point, so you can get a feel at a local level for how this works. And then we can dig into AWS and we can dig into all of the architectural bits of that next. So the first thing I just want to get clear is a little bit of Exercism terminology. So when you're looking, if we look at your exercises, when we're looking at these exercises, these are exercises, that's what we call them. Other websites call them different things, we call them exercises. But once you start an exercise, so as soon as you click in and it's in progress or it's published, under the hood we create a solution for you. Even before you've actually solved it, as soon as you're in the editor doing anything, you have a solution. And so you have one solution to every exercise you've ever either downloaded is one trigger or started in the editor. That solution then has in it multiple iterations, which many of you will be familiar with. If I look at Tufa, we've got 2 iterations that are going to be blank. The data on my, let me go onto a real machine here. So we have 4 iterations on actual Exercism, which are the different versions of this that I've published over the year. So we've got one solution with multiple iterations. But really what an iteration is a wrapper for a specific submission. And these are the 3 different terms you need to remember. And that's basically all the terms you need to remember today. You have a solution. Every time you run the tests in the editor, or every time you upload via the CLI, you create a submission. And whenever one of those is a sort of important point, and that's either when you submit in the editor or when you upload via the CLI again, you create an iteration. So iterations are save points, solutions are a relationship between you and the exercise, but then submissions are where we're going to be focusing today. So if I come back over here, click open in editor, if I just click run tests here, what's happening here in the background is that this is creating a submission in the database. You can have as many submissions as you want. They pretty much never get deleted. I don't think they ever get deleted. Every time you hit run tests, we're just saving a submission in the database. And what that does is it creates a record in the database, but it also takes the files, in this case, Tufa and also bizarrely lasagna, ignore the lasagna bit. It takes those files and it writes them both to S3, which is where we keep them as a permanent storage. But it also writes them to EFS, which is Amazon's elastic file system, which we're going to be talking a lot more about as well. So creating a submission is pushing your code to us creating a database record, and then us saving some files both in S3, which is just Amazon's big storage world that we save them permanently, and then also we save them on a local hard drive. That's the basics. Then a lot of other stuff happens. So we notice this submission's being created, and we know that when submissions are created, we need to run test runs for them. If they're iterations, so they're like major submissions, or in fact, I think just if they pass the tests nowadays, we'll create analysis runs for them where analyzers run it, and we'll also create representation runs where our representers look at it as well. And I'll go into a lot more detail about that in a minute. What happens when we create a test run? That's the one we're going to start with. So when we create a test run, we put the solution, the submission rather, into a queue. It's in Redis, and again, I'll go into all the technical detail in a bit. But we queue that up in Redis as something that needs running. We say it's this submission ID, it's a test run, and we also say some other stuff about the version of the exercise, and that's saying we're going to go into a lot of detail in as well, because that's really useful for maintainers to understand. And then I've just realised, I'm just going to pause, I just need to hit the start event button in Discord. Oh, it is already happening. It's magically run. Good. So we've queued the submission up. It's gone into Redis. And we then have a piece of tooling called the tooling orchestrator that is looking at that queue and saying there are these things that need running. And then we have a whole suite of machines that we're going to look at again. Those suites of machines come in and grab each of these different requests that are coming in, each of these different test runs. They execute the code, and then they push it back to the web server and say, here are the test results. Those end up piping back through, and then they end up via WebSockets back into here. So that's my super high level introduction to everything. Does anyone have any questions about that? Does that sort of make sense at a very top picture? Have I said anything that's thoroughly confusing? I'll just take a swig of coffee and wait for the comments to catch up. I would love for there to not be this 30-second lag between me talking and the comments, because it does make it quite difficult to read them. It's one of the nice things that Twitch has over YouTube, where Twitch is basically instant. There's no lag at all. But on YouTube, you get this lag for 30 seconds or so between you streaming and anything coming back, which is definitely a bit frustrating. Okay, Robin says it all makes sense so far. Thank you, Robin. Okay, good. Okay, so let's look at a little bit of code. I'm going to presume you understand sort of basics of SQL and probably that you know what things like Redis and everything else are. I'll very briefly touch on them, but I'm going to presume that you have familiarity with that, so I don't end up spending absolutely ages talking about stuff. So let's open up a terminal. Nothing more fun in life than having a terminal open. I'm just going to refresh this so we stop getting history of things. Okay, so let's clear this. So we're going to hit run tests, and this is just running on my local machine. We'll look at the same thing in production in a minute, but a whole load of stuff happens, as you can see, and I'm going to talk through what this looks like. Let me turn the font size up a little bit. There's a lot of stuff to look through. If I turn the font size up, and I lost where I was. Hold on. Let's just do this again. Blats that down a bit. Okay. So, first thing that happens when you hit that button is you're sending a post request to one of the web servers. We've got a suite of web servers, and I'm going to show you some of this stuff on AWS at the same time. So if we jump into Elastic Container Service. So we run all of our web servers and stuff via Docker. You don't need to know too much detail about that. We have various different things running, but one little fleet of things here is our web servers. These hit API, any cable, which is for WebSockets, and also the actual website servers. Because this hits an API endpoint, it's hitting our API fleet, and in here we have I think we just have three machines that run our API that sit here. We can look at logs of these things. I have to zoom back out a little bit so we can make sense of this. Yeah, all of these same requests that you're going to see here would be coming into these API things. There's a whole load of stuff here you can see. So I'm mimicking that locally by just having a local single web server running that's just running all this stuff. But what you're seeing here locally, we could jump into a server and look at the logs there. So when you hit run tests in that moment, you're sending this set of parameters to the web server. You're sending a hash with some files in, and there's 2 files, and at the moment there is twofer.rb, which is this first file here, which has just got a load of blank lines, as you can see. And this is an exercise file, and I'm going to talk about this in a moment. We have different types of files. And then we also have this random lasagna.rb, which is just because I've got bad data in my database locally. That doesn't have anything, but you can see we don't really know what it is, so we're just saying this is a legacy file. Let's just hide this. But what's useful to understand here is that's mimicking the same thing as when you submit via the CLI. When you submit via the CLI, we package some files together and then we upload those. And they're hitting a slightly different endpoint. I'll look at the code for that in a moment. But fundamentally, they're doing the same thing. They are... I've made the font size big and now I've lost where I am again. This is annoying. Sorry. Okay, let me just get this back up. Have 8 blank lines in here instead. Okay. So, yeah, I want you to understand that the files that come via the CLI are exactly the same as the stuff coming into the editor, which is why it's always really weird to me if there's bugs that only happen via the CLI and not the editor via test runs, because the actual process that we go through here is basically the same. So now we do a whole load of stuff that you don't need to worry about. It's not particularly relevant to this. We check to see if you're a spammer, basically, of which we get lots. We get various bits of data out. We can ignore stuff. But then, and I'll pull up some code here at the same time so we can actually see what's happening. So let's make this a bit bigger. So if we look at the controller where this is coming in, which is, I believe, solution submissions controller. So we're creating a submission here. So as I said, we get these files, we do some Ruby mapping, and then we're creating this submission. And this is where things start to get interesting and where things start to get kicked off. So if we look at what this looks like, so we have a create method here. We take the solution, we take the files, and then we're also taking whether it's submitted via the API or the CLI. You'll always find if you read Exercism's code base, there's lots and lots of wonderful to-dos. The optional ones are ones that are just improvements that I don't think are going to hurt us. But yeah, you'll find various things. Anyway, we then do a series of things. So we have some guarding. One of the things we do here is we checked that the new files are actually different from the old files. What we don't want, a nice sort of denial of service attack for us, would be if somebody could just keep on submitting the same files over and over and over again. That would be a bad situation for us. So we check first of all that the files and their digests are actually different, and we raise an error if they are. There are some problems with this. So if tests fail, then actually you just want to be able to resubmit the same files, and currently you can't do that, which is a bit annoying. But there's other solutions to that other than this. And then we create the submission, which is just creating a bit of data in the database. We then create each of the files. So this does a couple of things. This firstly creates, we get a S3 path, which lives in a bucket, which is our submissions bucket. And we pop the file up in S3. But we also write to EFS. And this is a good time to talk about EFS. So EFS is Amazon's elastic file system. You can basically think of it as a giant hard drive that has infinite space that you can just mount on every machine. It's a networked hard drive. And you can just use it and access it just like any other hard drive. But one of the things that we do, and we use this in lots of places, is we use it as a shared storage that different machines can read from. So we keep all of the different repositories, we keep all of the student submissions, all of this sort of data on this file system. And then we give different permissions to different machines to be reading all of these all of these files. And it's a very, very fast way. It's much, much faster than taking data to and from S3. It's a lot easier as well than having to pass files around. You don't want to have to be passing files through HTTP requests, especially if they're quite big. That gets quite painful. So we sort of use this as it's a really nice, easy level to write to EFS. And we have a few different EFSs, Elastic File Systems. We have one for repositories, which we'll talk lots about. We have one for submissions. So we make a directory for this submission, and we submit each of the files in there. We make sure that they're valid Unicode. We convert it to UTF-8 before we write it. But that's basically it. You don't need to know much more about this. But crucially, what we have now is a database record that refers to this thing, and then a file for each of these, for each of the files that you've uploaded. And then we initialize a test run, which is the meat of where we're going to go. I'll very quickly just show you a couple of other things. We also schedule any jobs. So you see this a lot throughout Exercism's code base. We have lots and lots of background jobs. Background jobs are a massive part of how our whole infrastructure works. We use Sidekick. You can see we've processed 180 million jobs since we launched Sidekick. If you look down here, you'll see flittering away over time jobs that appear down here. But Sidekick basically just handles all of the you don't actually see many of the jobs here because most of them execute so quickly they don't actually reference. You just sort of see this number here going up slowly over time. But we have a whole load of jobs that are piped through. These are the ones that fail. And those jobs just basically push things out of bounds. So the 20 have happened in the last second or so. Just watch that number going up. And so one of the things that we often do is for things like when you submit a submission, we might want to award you a badge for that. There are various badges you might get awarded. Submitting something is enough to get you the rookie badge. So we queue up a job to check whether you get the rookie badge. But if you publish a solution, you might get another badge. If you finish a mentoring solution, you might get another badge. So all of these different things just get queued in the background, and we just leave that to run. We have different queues with different priorities that things get pushed around. And we also log metrics. And metrics are stuff we don't use too much. But if you look at Exercism and look at the About Impact page, you can see here that we have a live graph of things happening. And these are basically every time, it's not submissions, I think it's when people publish iterations, I can't remember. But things anyway appearing on here whenever people do stuff. So somebody's just completed COBOL, someone's published a new solution over here. So you can watch this map, it's quite fun. It's just About Impact. And you can see all the various bits and pieces that are happening and who's doing what. And that metric bit when somebody submits a file is a really sort of the key bit that underpins that. It's the bit that starts off and triggers that thing. I'm just going to take a sip of my coffee and read the comments. Okay, Sebastian asks if there are any languages that require unique infrastructure. So every single language has its own test runner and its own analyzer and representer that's written in that language. We'll look at those in a moment. Nothing requires its own underpinning infrastructure. We run everything on the same set of machines, which is one of theoretically the nice things about Docker. Although we are starting to see quite a lot of issues with Docker with I can't just make a Docker file on my machine, which is a new one of the Apple Silicon Macs, and push that up and have it run on AWS because it complains that it's been built with Apple Silicon, not Intel Silicon. So Docker's maybe not quite as perfect as it seems to be. But yeah, we'll look at all of those infrastructures in a few minutes. So this is now the crucial bit. So we've got these files on a hard drive. We've got some data in the database. We're now creating a test run. So if we look over at what that looks like, we are creating a test run, and there are three. I have a very sticky touchpad. There are three parameters that we take. The one is a submission. The next one is the git char, and then we also have a flag for whether we should run this in the background or not. And these are going to be really, really critical. And a lot of the pain that we have in this whole setup comes from this git char flag, which I'll come to in a second. But just taking our starting path, we're just initializing this with the submission. We didn't pass either of these things in. So basically we just fire off at this point, this tooling job create. I'll look at this in a second. And then we update the status of the exercise. A submission has various different test running states that it can have. I've not used this touchpad for years, and it's showing its age. So yeah, submission can be in various states. It can be not queued, which is its initial state. It can be queued once we've done this little bit of a job here. And then it can be passed, failed, errored, exceptioned, or cancelled. Passed means the test pass, failed means the tests fail, errored means the tests errored, and exceptioned means that something went wrong that we don't know about. So maybe it timed out, maybe it just blew up in some other way, but it's sort of an unpredictable field basically. If there's something that we're not expecting, generally at an ops level, it could even be that the results.json isn't valid JSON, so when we try and parse that at the end of it, it breaks. So we set the status here, and we move this submission just to say it's change its status to be queued. At this point, I just want to talk a little bit about this git char, because this is something that underpins a whole load of Exercism. So you probably all know, maybe you don't, but let's look at Python actually, because this is a good example of where we had this recently. So every language on Exercism has its own Git repo. And this Git repo has in it exercises. It has in practice exercises, maybe Bob. And in here we have a whole load of files. Now, these tracks are updated like all the time. If you look at Python, for example, you know, every day it's being updated. The 14th, a whole load of stuff got merged. Most of the stuff that's happening here doesn't affect all of the exercises. And so it's important that we're able to understand what's actually changing in this repository and how that affects things. And why this matters is that it's really important that as a student is solving the exercise isn't changing underneath them. You can't be solving an exercise and suddenly Bethany merges a PR in Python and that exercise has got an extra test case that wasn't there 2 seconds ago. And equally, you don't want to solve an exercise, have it all working great, and then suddenly find that your solution no longer works because somebody's added an extra test case. So by every solution, so if you remember, your solution is the relationship between you and the exercise. In every solution, we store the git char that is of where the repo was at last time when you started that exercise, or later if you update the exercise, which I'll explain. So as soon as you start an exercise, we lock the git char of that exercise to the point in time of the Git repository. And then we guarantee basically that whatever happens in our infrastructure, you will always get that version. And so one of the important things, again, about the way that we use EFS is that we store all the Git repositories in EFS as Git repositories. So we don't materialize the Python track into EFS. We have the Python track as a Git repository. And then whenever we do anything that's about your solution, we check out whatever commit is relevant to you, and we act on that commit. So you've got a Git repository there that is constantly, every millisecond, being checked out to a different commit to a different point in time for every student that's using it. So when I open my TUFO and click open an editor, in the background, we're getting the actual commit from the, in this case, Ruby track, from the Ruby GitHub repository that I am locked to, and that's the data it's showing me. When I look at the tests over here, I'm seeing the tests. This file is being read from the git char that this exercise is locked to. So this is really, really powerful, but it's also really, really complex. And one of the downsides of this is that we also want students to be able to update to the latest version of the exercise. And this is a really normal thing. There's a new test case added, the exercise evolves, this happens all the time. Students want to be able to make sure that exercise still passes. They want to make sure they're still doing a good job with their code. And so once an exercise is out of date, I don't think I have any on my local. Let me see if I've got any exercises that are out of date that I can show you. Where do I look for this? Here. So gigasecond, you can see this little triangle is out of date. So we get this nice little pop-up here. I can click on this and it shows me what's changed in this exercise, and I can update it. But this is a really annoying example. And I know Bob Hop's watching this. Bob Hop's solved, I don't know how many, 1,000 exercises, Bob, on Exercism. And if every time there's something like this changes, which doesn't really affect at all whether your solution passes or not, this is just sort of an implementation detail of the tests, then that's really annoying, because you're going to get thousands of these modals, these pop-ups that you have to click. And so a little while ago, maybe a year ago, we evolved this slightly. So you no longer have to, we no longer just look at the Git char, but we actually look at the files. And we look at the files and we understand if the files have changed. And so we say, we'll only ever prompt you about this if the test file changes. We won't prompt you if the stub changes. And we won't prompt you if some meta file you don't need to know about changes. And so we have an extra field, and we'll talk about this in a bit, which is called the Git important files hash. And we have a group of important files. We look at the hash of those files, so the contents of them hashed, and we say, okay, have those changed? And if they have, then we'll show you something like this. And if they haven't, we won't. And that solved a lot of the problem, because it meant if we change a meta file or something else, then we don't need to show you. But in this case, the tests have changed. And this is really problematic, because we don't know that this little skip change is meaningful or meaningless. That's an implementation detail in that language. We've got no Exercism way of knowing that. And so what we have to do in this situation is actually rerun the tests. So when this change was made to gigasecond, what we've then had to do in the background is go and run the tests of every single gigasecond Ruby submission again and see what's changed. And if the tests pass, which they will do here, this will make no difference at all, then we automatically update that solution to be the latest Git char. We say this, your exercise still passes the latest Git char, we're just going to roll you forward. If you fail, then we're not going to do that. If you fail, we're going to show you this modal again. And so going back to the code and why we're talking about this, one of the things you'll notice here is that we also set a couple of other statuses, and you'll see these other statuses at a solution level here as well. Is we have an extra field that we store for whether your published iteration passes the latest tests and your latest iteration passes the latest tests, as well as just whether you pass the tests at the last point you actually submitted something. And so we're managing all of these three flags. And every time we're running the tests, we have a whole load of side effects that we have to look at as to whether it affects the latest, the published, the current, and it's a really confusing set of things. And we deployed a load of stuff last week that's really improved this, and I think is working great. And if I've got time, I'll talk you through all of that as well. But one of the important things, and for maintainers, we added this new flag last week that says you can also now merge something, and we'll see, let's find an example from Python. So let me see if I can remember where we did this. Maybe this one. Yeah. So you can see Bethany's merged here, and she's put this little flag into the commit message. And if you're not used to Git commit messages and the way GitHub does stuff, this is a way that things often work. Sticky trackpad. You can put little phrases like this into your commit message that have sort of superpowers. So you can type skip CI into your message like that, and then the CI won't run for that commit. And we're using this flag, which I know some people dislike. But this effectively tells our system that we don't need to rerun all the tests again, and that we can just wave that through. So I could talk lots about this, but I want to get a bit more into the infrastructure side. So yeah, let me just check to see. Yeah, there's no comments about this. That's fine. I'll keep going. But if we want to dig into this a little bit more later, if I've got any voice left, we can do that. So let's follow our critical path. So at this point, we are doing tooling job create, and this is a glass of water in the way. In a totally different project, if I remember rightly. So this is where we start to move away from the website. So everything that's happened so far is happening on the website in the API call, effectively. This is where we start to now trigger stuff in other bits of the world. So here we are putting together a hash, basically, a dictionary in other languages of some information. So the submissions ID, what type it is, so a test run, the language, the exercise, a timestamp. And then we throw this into Redis. And there are two different queues that we can throw it into. We can throw it into a background queue, or we can throw it into a normal foreground queue. In our process right now, it's just going into a foreground queue because we need to get the response quickly. And so we go into Redis. Redis multi is like a transaction, basically. And it's not really a transaction, but it's sort of like that. And we push a new thing onto the queue. We push a couple of bits onto the queue, actually. We push into the queue key to say there's a new job, and we also actually put some other information on as well. But you don't need to worry too much about that. And so this is the first point that now pulls us out of this world. And so at this point, we're gonna jump into the actual one of the machines and see what's happening over there. So, anyone got any questions, by the way? There's no questions in there at the moment, so we'll come back to this. But please do write questions. So we now move outside of Docker, and we're into classic EC2 territory. So we have various EC2 instances running. So for those of you that don't know AWS, EC2 is a series of is their platform for basically just running servers, just traditional servers. You can, if I come into here, you can choose what you want: Ubuntu, Amazon Linux, Mac OS, a bazillion other things. Choose what size machines you want. Do you want to spend £1 bazillion on something crazy? One of these things, I don't know, $17 an hour for Windows. You can spend a lot of money very quickly. A whole load of stuff, none of which you should be manually clicking around with. You should use Terraform, which we can talk about. But these are our machines. We have 3 machines, a Bastion, which we'll look at in a second. Something that runs private GitHub actions that we want to run on our own infrastructure rather than on Amazon's infrastructure. And then our discourse forum. And then we have a whole load of auto-scaling test runners. And these test runners are the bread and butter of how we run tests, auto-scaling tooling runners. So let's take one from the middle. You can't, please don't all try and connect to this machine. You can't connect to it, I hope. So let's jump into it. Okay. So I'm going to jump into this machine. These machines are all T3 mediums. So if you're interested in what the underlying architecture is that the test runs and everything else run on, you can go and look at what a T3 medium is. The machines last for a day. They're all part of a auto-scaling group. So you can look at that over here. So at the moment we're running 12 of them. It changes depending on what we do. They automatically scale up and down and in and out, basically. So if we look at, I never know where the thing is. Here, monitoring maybe. Nope. There's a log thing somewhere that tells you activity, probably. Yeah, so you can see they get replaced at various times. So one got replaced at 8 o'clock last night was the last one that got replaced. So they're all quite close at the moment because I rebuilt the whole fleet recently. But I like to try and I often just turn them off at random times just to try and spread this out. If the machine is running low on resources, it starts to misbehave, it will get shut down and it will get replaced. Otherwise, they get replaced every 24 hours anyway. The reason they get replaced is that Docker just cannot cope. After about 48 hours of doing what we're asking it to do, Docker just stops functioning, which is weird, but it's what happens. So let's have a look on one of the machines. So let's jump in by first of all looking at the actual invoker. So these are test runs that you are seeing. They are happening. This is real time. These are different test runs that are coming in. So while we've been sitting here, we've had a Java log levels one. We've had a C# phone numbers one. We've had a JavaScript freelance one. And we'll look into all of these in a second and see what happens. You can see how long they're taking to execute. So they're taking 5 seconds. This one took 2 seconds. This one took 2 seconds, 3 seconds. And you can see this is how long it takes in Docker. And then this is how long the whole thing takes end to end. Some of that end-to-end stuff happens like after the message has been sent. We only take, I think we take about 1/4 of a second on top of the actual Docker bit for infrastructure stuff. But these are different jobs that are running through. And you can also see these jobs in CloudWatch. If we go and have a little look over here, these are our different log groups. If you look at this, you can start tailing this. And this just logs every time something comes in. We log the ID, the submission ID, the test runner, the type rather, language exercise, and then the status. So 200 means that it completed successfully. That might still mean the test failed, but the test run completed successfully. The duration, and then the instance ID. So each of those instances has got an instance ID, and this enables us to jump in and have a look at the logs and see things. So let's cancel that, but we can dig into some of these in a minute. So what's actually happening here? Well, we have 2 services that run on this machine. So the first service is this Exercism invoker, tooling invoker. You can look at the code for this on GitHub. And I'll show you what this does locally. So this is the tooling invoker locally. If you ever want to run these up locally, it's a load of work to install, but you can just, if you do get it going, just do bin dev and that will start a thing up. And what this is doing is it sits there and it basically is pinging every 10th of a second, every 100 milliseconds. It pings and says, is there anything for me to do? Is there anything for me to do? We did originally build this using 0MQ and some other stuff, but in the end, I just had reliability things, and so we just stopped doing that. But what you'll see is it's pinging something called the tooling orchestrator. And you can see it's pinging it because this is just sitting here. Locally, it runs, I think, once a second. But this is just sitting here getting a load of jobs, saying, no, there's no jobs. It returns a 404 each time. It takes like 3 milliseconds to do this. And what this is doing, this tooling orchestrator, this is looking at that Redis queue, and it's just basically peeling stuff off that Redis queue. So it's really simple code. We can have a look in retrieve next job. So we have this web application. This is like beautifully simple. This is the endpoint, jobs next. We ask this to lock the next job, which basically proxies in through to here. If we find it, we return it out as JSON. Otherwise, we return a 404. And if everything suddenly goes bad, we start 500ing. But here we are. We have 2 queues. A queue, the queue and also a series of things that are locked. We simply pop off the first thing off the Redis queue, and then we push it onto the locked queue. We go and find it effectively by getting more data out of Redis, and then we push that out, as I say, instance JSON. So if you remember over here, all that's happened very simply is we've taken data, we've written it on the web server into Redis, and we've got another thing over here, tooling orchestrator, which is pulling things back off on request. And again, you can just have a look at the code over here if you want to. It's all just in lib orchestrator. There's only like 5 files in here. And we have some other stuff about requeuing jobs and other things, but yeah, it's that simple really. So this tooling invoker is pinging away. So going back onto our actual production machine, this is just sitting here, ping, 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 waiting for something. It gets something and then it runs it. And obviously the running bit is where the interest bit for a lot of you is going to come. So we'll dig into that in a second. But let's just have a little look at a really high level what happens here. So we've got this job. Let's find a test run. So Ruby hello world couldn't be simpler. So this creates this directory here. And so I'll talk a bit about it. I'll show you a test run in a second, but just to look at what it does. So who am I? Okay. So if we look in this directory, we get 2 things. We have a Exercism output directory. This just has stuff that we do. So we have any standard out gets captured here. Any standard error, there is none for Rubies. We also have though the results.json. So here somebody's managed to add a syntax error to their hello world in Ruby somehow by not just changing the sentence. I'll never understand how people manage to struggle with hello world so much. Yeah, the results are getting written out to this. So if we look at any of these different things, if we look at this one, for example, we're always going to see this results JSON. And so this is a failure in JavaScript. So you can see for each one, the first test has passed, the next test has passed, but then presumably somewhere we get down here and a test is, there you go, failing at the bottom. So somebody hasn't quite worked out how to do the monthly discount bit, which is complicated. I'll give them credit for that one. So this is the spec that we'll look at in a second that powers what you see in the test run at the other end. Okay. So the other job on here, just before we look at stuff, is a manager. Now, this manager is basically running through every single different type of tooling we have on Exercism. And so again, just presuming you're not familiar for a moment, if you have a look at here, go to repositories and go to test runners, you can see we have a test runner for every language. About half of these are written by Eric and the other half are written by maintainers, wonderful people like the people watching this. Each of these is its own thing, generally written in its own language. This is written in Rust. If you look at the Go one, it's written in, doesn't have a source directory for a start. It's written in Go, etc., etc. And so each of those is responsible for following this, which is the test runner interface. And you can have a look at this at in Exercism docs. And what happens here is that we build, let's take a look at the Ruby test runner. So we have a Docker file. If you're not familiar with Docker, it's not scary. It just basically tells you how to build a machine. And then we run this bin run sh. This tracking pad is very not good. Which just calls run with 3 arguments. And these are the same 3 arguments that we see here. So the first argument is the slug of the exercise. This is important because we need to get the right files and do the right things with it. The second one is a path to the input directory, which is where the student's submission is. And then finally, we have a path to an output directory where the results.json should be written. And as this says, the test runner is responsible for doing one thing, which is for writing a results.json and doing it as quickly as possible, and then returning with an exit code of 0. And there are 3 different versions of the results.json. I won't go into too much detail on this now. Everyone that's built a test runner knows this, so they don't need me to go through it all. But effectively, as I just showed you in that JavaScript one, we're looking to see whether tests pass, fail, or error. And then we're looking to see as a whole whether the whole suite has passed, failed, or errored. So that's the responsibility of each of these individual test runners. So this log here that I'm showing you, this is going and it is getting the latest version of each of the Docker files that get built. So the Docker files get built by GitHub Actions, and then they get put up into our own private world, which is over here in ECR, Amazon's Elastic Container Registry. So each of these lives here. If we look at the Gleam test runner, I'm going to pick on Gleam as they've been releasing a lot recently. All of the different sort of things they release all get pushed up here. And then the latest one of these gets tagged with production. This is how Docker works, is every version has its own tag, and then you also have a latest or a production or something like that tag which you can then reference. So over here you'll see we are going and saying, okay, get me the latest production, or get me the production version of the Common Lisp Analyzer from our ECR. We install it, it looks, it says, okay, the image is up to date, there's nothing to do. So every minute we're just basically, and then it will pause for a minute and then it will go again. So when you deploy a test runner, what's actually happening, and we can have a little look at the CI. So if we look at the deploy bit, so we log into ECR, we build the Docker image here just by calling docker buildx build. That just does whatever Docker needs to do, and then we go down here, and then we push it to AWS. So that gets pushed up, gets tagged as you've just seen, and then sometime within the next minute, each of the machines will notice that it's changed and will update it to the latest version. And so you could just tell this log, and if somebody pushed right now, you would then see it pulling a couple of layers and downloading. So if we have a look on this, what's that? Yeah. So these are all of the different Docker images that are installed on this machine. So every single one of these EC2 tooling runners, each of them has all of these individual Docker files installed in them. And you can see that the size of these Docker files varies wildly. And so those of you that are active on Discord will know there's been a lot of conversation recently about the different sizes of these files. Some of them are, 100 meg. Some of them are 2.1 gig, 2.5 gig rather. And that was 4 gig, so that's already nearly halfway down already. So Meatball's been doing a great job of reducing these. Eric's also been working on that. I know other people have as well. Thank you if you've been doing that. It saves us hard drive space, which is weirdly one of our bigger costs on AWS. You can also, we can see how much we have. So we're using 44 gig and we have 82 gig available. When I set this up, we were using like 80 gig just the whole time and peaking to 120 gig, which is why the file size is the size it is. So we can basically reduce this down probably to like 50 or 60 gig at this point, and save ourselves loads of money. So that's good. Thank you. There's a question. Cool. So I'll answer Francisca's question and segue at the same time. So one of the restraints that we have on this is because we have this suite of machines, there are say 12 machines running, we only run one tooling job at a time. So we run sequentially, we don't run in parallel. And one of the reasons for that is when we used to run 3 jobs on a machine at once, or these could just tick away, we discovered that in doing that, some languages require quite a lot of memory. So each of these machines has 4 gig of memory, but I think maybe .NET, maybe Java, I can't remember, things that have got big underlying, not VMs, whatever the word is that I'm looking for. I have lost the word. Frameworks, still the wrong word. Languages that have got those often need to consume quite a lot of memory to do the compilation step. And we were finding that if we were running like 2, say, C# ones at the same time, rather than halving the time of each of them, it was actually massively reducing, massively slowing them down, massively increasing the time. A lot of languages still really struggle to be quick. You see that variance if we scroll back up to when we were looking at when we were looking at these. You've got some that are consistently 2 seconds. This has taken 20 seconds for this one. 1 second, 3 seconds, and these tend to be quite consistent. Like all JavaScript ones take about 3.5 seconds, as you can see here. Like they're all in that region. All Python ones take like half a second. So there's a lot of variance in languages. And so Francisca's question was, why did Kotlin become available? Simply because before that we had no way of getting it under 20 seconds to run the tests. And I think either there was a new version of Kotlin or someone came up with a different way of doing stuff. I don't know. But that meant that we were able to get to the point where we could push that live. But performance is a huge thing, and often new releases of languages, I can't remember what it was. There was something that came out a couple of weeks ago, brand new version, supposed to be much better. You just added an extra half a second onto the test runs. So it's very frustrating, and it does feel like you're constantly doing a lot of shortcuts and a lot of different things. And sometimes there's underlying other issues with that. So there was a question on Discord about why we had to do some special stuff for Elixir. And in fact, it's stuff we have to do for all of the Beam languages. So if we have a little look at this bit of code here. So this is a list of tools that are the special tools that need a bit of special treatment. And some of them don't anymore, actually, so they could probably change. But the top 2 are the ones that the Beam ones, basically, that need things. And maybe Erlang does as well. I noticed Erlang was slow earlier. Maybe we should be doing this for Erlang. But one of the things that we do is the Docker containers have no network. So they can't access the outside work. So effectively, we just don't give them a network device. As far as they're concerned, they don't have a network device. So if they try and do anything networky, the computer just can't do anything. So either it falls over and we have to write some code to fix that, or it just deals with the fact it doesn't have network. What we found with Beam languages is if they don't have a network device, they sit there for about 5 seconds scratching their head, unsure what to do. And they seem to sort of just presume that, well, they must have a network device. Maybe it's just not working. I'll try again in a few seconds. And they basically get into a loop of repeatedly pinging to see if there's a network device. And then eventually, after some time, I think 5 seconds or so, they give up. It might even be longer than that, might be like 10 seconds. What we found instead was if we give them a network device, but we give them this internal, this is just my name for internal, so it's a network device, but it doesn't have access to the internet. It only has access effectively to its own network that it's the only machine on. Then it's fine. Then it's like, oh, okay, this makes sense. I don't have access to the internet, but I'm on a network. I can cope with that. And so it just runs immediately. And so there's been lots of experimentation, frustration, pain that we've had to go through to understand some of this around these various things. And I'm sure there's tons more things like that if we really experimented with, we could find and we could work out. So let's dig in a little bit into this tooling Invoker, because this is the the main body of where we need to look at. So tooling invoker is, as I said before, over here. If you want to open it up, you can have a look with me at the code. And again, just to be clear, this tooling invoker lives on every machine. This is the piece of code that's just pinging, saying what's the next job I should do, what's the next job I should do. So have a look in here. We have a worker. This worker literally just sits there and works. It just sits in a loop and looks for jobs. Every 100th time it gets to the loop, it just pings out a message saying that it's alive. It traps signals like interrupt and terminate, and if it gets those, it finishes the current thing it's doing, and then it terminates. Pretty standard stuff. But this is the key thing. It retrieves a job. If it has a job, it handles it. Otherwise, it keeps going. So let's look at retrieving a job. So this quite simply pings our orchestrator that we've already looked at with this endpoint that we already looked at, gets this JavaScript back that we've already looked at, and then builds a job. And this is building either a test runner, a representer, or an analyzer job. If we again just look at a test runner job, the 3 arguments that get passed into the Docker file. So the exercise name and then the directory. At the moment, we use the same input and output directories, which is this. And so, to be clear, on our machines, if we exit back out of this. So going back to this job you're seeing here, this canary job, this is mounted on inside each of the Docker containers as this. So as far as a Docker container is concerned, their world lives at mount exercism iteration. As far as this external machine, this tooling machine cares, it lives at this directory, and a new directory is created for every job. So if I forget which user has permission. If we look at here, these are all the different jobs this machine has run, lots and lots of them. Each of these is just creating this directory and then getting mounted. That directory is getting mounted on the machine at this point. We also specify what output file paths we should get. These are different for different pieces of tooling. Say for test runners, it's results.json. If we look at a representer, you'll see we actually have 2 files, I think, that come out, 3 files that come out. A representation.txt, a JSON, the mapping. So these are the files that we need to extract back out of the container afterwards. So this is just a bit of setting up some stuff. And then we create a new job, fine. So that retrieves the job, sets it up, and then we handle the job. And so this is, we process it, we check to see if it's got an abnormal status, and if so, we check our canary. I'll talk about that in a second. And then if we're good, we fire this back to the orchestrator writes it back to Redis, that pipes back. We also write out to CloudWatch, do some other stuff. I'll come back to the canary stuff. So let's just have a little look at the job processing. So we process the job. So first thing that we do is we prepare the input. So this is where we're creating this opt jobs thing, these ones. And we create some files, but then the real stuff happens here. And this is where it sort of gets a bit more interesting. So we find our EFS path for the submission, and we also find a path for, so we copy the submission files and the Git files. So we start with the Git files. So we go into the Git repo. So if you have a look on one of these machines, we have mount EFS repos. So these are all of the different Git repos we have. So if you have a look at, let's take Go for example, this is just a Git repo. And it's in I can't remember what the type of repo is, but it's a type of, it's like the Git repo but not unpacked. So it's effectively like the contents of the Git directory, but just that is the whole thing. And so this is, again, on EFS, we have these. These are shared across everything. And what we do is we get the git char that I talked about earlier. And then we go in get the path at that git char. And we look up the entry of that OID. So this is just like git internals. You can work this code out later. It's not that interesting. But effectively what we do is get all of the files from that git char. And we get them and we just we write those files. And so we're doing that for each of the exercise file paths. So back when we were in website world, over here maybe, where do we do this? I'm trying to remember where we actually create these file paths. I don't remember. Let's git grep this and find out. So there we go. Okay, fine. This is wrapped. That explains. I can't type. What's it? Tooling. Okay, this is better. So when we created the job in the first place, I thought I'd missed this bit. This is data that we're specifying that the tooling job is using. And we specify the git repo, which is the slug of the track. So go in this place. The git char, which we saw when we passed in. And then also the directory within the git repo. So the exercise directory. And this is another thing that feels like it should be really simple. Like we just specify, okay, well, it's the, let's think of a good example. The matching brackets exercise. But some of you will remember that the matching brackets exercise changed its name. I can't remember. I think it's actually changed from matching brackets to something else. But so you end up with a problem, because when an exercise changes its name, the slug of the exercise no longer actually matches the whole in the path. So one of the other things that we have to do in the database is store the git slug as well that the thing is locked to. So if we have a little look at the last submission we did, so this is in the website. So not only are we storing the git char, but we're also storing the git slug. So we're also saying, okay, when you build paths that you need to get the right files from Git, this is the slug. So when we rename exercises, there's this whole extra level of complexity that has to automatically be managed. And this is one of the things. So anyway, probably too much detail. But we also get this valid file paths from the submission file paths thing. And this is also another layer of complexity that we have to deal with. We look through each of the files that someone uploads, and we determine whether or not it's a valid submission file path. And I wish this trackpad was less terrible. So there's a whole load of stuff we won't let someone submit. We won't let people submit things in Meta. We won't let people submit things in Docs. We won't let them submit approaches or articles or things in .exercism. We don't let people override editor file paths, and we don't let people override the test files either. So although we can't guarantee people won't do this, so people I think can submit via the CLI pretty much whatever they want. When we actually look at the code and we show it in, I think, the website, and definitely obviously as you're seeing when we're passing it through into tooling, we have these guards that make sure that files that we know should be sort of protected don't get overridden. So all of this gets put together anyway into this data key that gets passed in, and that gets passed all the way through. And so eventually we end up over here going through each of those exercise file paths that we saw, and then looking them up within this Git repo, and then also looking up all the submission file paths. And because they're just saved in EFS as well, we can just go in and we can get that. Now, one thing you definitely shouldn't do is, you'll notice that I just did a nice ls on repos. If I did ls, or even worse, double tabbing on the submissions one, we end up in really problematic territory, because that ends up with absolutely tons of things, millions of submissions. But if I have a little look and just look at say my own TUFA, oops. Okay, this is my own TUFA, and we have a little look at that. There you go. So we can see that all of the different files that get submitted just get added into these directories and written down. So every single submission in our database, of which there are a lot. Somebody recently didn't believe that something like this is slow. So this is just count asterisks in MySQL, and it is really slow, which is one of the reasons just databases are hard. So this is going to come back at I don't know, 10 million or something probably. But yeah, for each of these things, all of those files are just written to our, is that 27 million? Yeah. So there's 20, so yeah. So this, now what I should have done is shard this directory. This would have been a sensible thing to do, but I didn't do that. So this directory just has 27 million subdirectories in it. If you know anything about anything to do with anything OPSI or anything, knowing that you have 29 million directories in a directory, you can probably all feel is terrible. So yeah, at some point I should fix this, but right now there are just 29 million subdirectories in that EFS submissions directory, which is why double tapping tab is really bad. And also why doing if I did du and include /mount, which is just the default, because I often just do this, which just tells you, the where the hard drive space has been used. That will just blow up very badly because it tries to look at disk usage across the whole of EFS. So yeah, it's fun. You can, I think, though, do you can do this, and yeah, you can see there's 8 exabytes free on those two mounts right now, which is always quite a fun number. But yeah, we're using 400 gig now of submissions. So we've used apparently 1% of EFS, which is pretty cool. Yeah, looking at the comments. Yeah, so no, MySQL doesn't. MySQL is slow. There's no. You can try it as soon as you have more than 1 million records in a table. It gets slow. Until 1 million records, it's fast. In Postgres, it's fast as well, but not in MySQL. It's just a known thing. I'm just gonna check. Yeah, and it's a bare Git repo as well. Yeah, that was the phrase I was looking for. Thank you. So, okay, so where are we at? So we've got we're over here now. So we've got those files. We've copied those files out of EFS. We've put them into this opt directory. So if we look back at, let's go back into a job. Let's cd into here. So if we look at this, we've got the files that you would expect. This is JavaScript. So we've got, these are basically the same files that you would find in the Git repo for this. So if we look at JavaScript, this is a different exercise, but you'll get the idea. You have these same files. You've got meta, you've got package.json, you've got these different things that end up appearing in here. So these are the files that have got copied over. And I think we have, we give maintainers control over which files they do. So what is this freelancer? Freelancer rates, that's concept, isn't it? This is where maintainers probably remember better than me. Or do we just copy everything? No, by the look of it, we just copy everything, don't we? Yeah, fine. So we don't copy docs, we exclude docs. I think we might exclude some meta stuff as well. No, maybe not. But anyway, this comes here, and then the students file gets merged in as well. So this will be the students file. Oops. Oh, sticky mouse thing breaking everything. Really annoying. Oh, really annoying. Yeah, so this is the students code, as you can see. So those two things have got merged together. That's the takeaway from this very long segue. I think I went on a bit there, sorry. So we've set up all our input files. We do have an issue that there's a slight race. It takes EFS like 100 milliseconds to propagate its files across the whole of EFS. So you can write on website, and then by the time you get on the tooling test runner, it actually can often start before those files are fully propagated. So we do have a thing that like sits there, and I think it has like, yeah, retries built in, and we just sleep for like 200 milliseconds, half a second, 1 second, 2 seconds, and until the files are fully propagated. It doesn't. It's not a normal thing, but it does happen. So cool. So we've now prepared the input, first thing, and now we call this run job command. And this is where we finally, after everything we've done so far, actually run Docker. This is the exciting bit. Here we create a container, label, and we create a thread that we run Docker in. We do all sorts of stuff for timing out, which you can read. It's probably too complex and boring. But basically after 20 seconds, we kill the thing. We capture some standard out, we captured some standard error, and do stuff that's OPSI. But this is the key bit. So all of this other code is just like wrapping a command, basically. Wrapping a command, making sure that we capture standard out, making sure we capture standard error. Have like kill things so that Docker doesn't just absolutely blow up. We also run with timeout with a kill flag. So all of this is what means that we reliably kill after 20 seconds, which we do. And we have to just be careful because the code can just overload the machine and start using all its resources. We sort of need these multiple levels of guarantee that a timeout will happen. But this is the Docker command. So if you ever want to run stuff locally and just do exactly the same stuff, you can do this. So we attach standard out and standard error. We have this really bizarre named flag, which is the stop timeout, which you would think would be like, okay, I want to stop the container after 20 seconds, but it's not that. It says that after you send it a SIG term, how long do you then wait until you then send it a sig kill as well? So how long do you switch from terminate to kill, basically? And if you set this to 0, it just immediately sends a kill flag, which is what we want. We then remove the container. So we have, if you see here, I think it's stats. No, stats. So we have no containers because they're all destroyed. So this is something to understand. This is nice. So you can see that container, it was born, it lived, and it died. So, and a lot of the time, because this just polls every second, and a lot of containers don't even live for a second, you can look at this all day and often not see anything. You only see it in that like glimpse of when something's going, if it lasts for longer than the 2 polls. What you can do, there's a flag. I can't remember what the flag is. All. Where it actually keeps, yeah, here you go. So it keeps things around after it's run them. So these are the ones that have been there in the last few seconds or whatever. The wonderful names that Docker comes up with. But it's not much use because it just shows zeros basically on things. So yeah. So we remove the containers afterwards. If we didn't do that, we'd run out of hard drive space in seconds. And we can't reuse the containers, because if we reuse the containers, they'll be left in the state that the previous person left them in. And because the person can just run arbitrary code, that's not a good thing. And that's the same reason we can't just use something like Lambda or something else to do this, because Lambda reuse containers and there's no way to stop Lambda from reusing containers. So all of this work with having these machines and everything is just because of this. It's effectively a really naive implementation of Lambda that doesn't have reuse. We then mount these volumes. So these are the volumes that you saw that we create, that we've put the files in, the opt jobs ones, and we just mount those at mount exercism iteration. We give this a label. We attach whichever network it's supposed to have. So we talked a little bit about this earlier. You have these 2 networks. I'll show you setup. So here we create, this is where we create this internal network. And it's just a network that is created with the internal flag. This just takes 120 milliseconds. We just do it when we create the initialize, when we start the service. But we either use network none, which is the default, or we use that one of those other networks, or that network. And we also have a maximum memory, which just defaults to 3 gigs. We then specify the image, which is one of those images that you saw running on here. So type representer production, TypeScript representer production, whatever. Whichever image is specified is what we call. And then the invocation args, which are on the job. And those are these. So this is calling it with the slug and with these directories. And then it runs. And it does stuff. So individual tools do individual things, but as we've seen, going back to our docs, the test runner is responsible for writing out a where's the interface gone? Writing out a results.json that conforms to one of these specs in this file. Something like this. An entry with lots of these in rather. So as soon as the thing finishes, we then have various so we have various statuses. If it exceptions, we call exceptioned on the job. But if we can I see that over here? Yeah. We have various different statuses that end up getting called in different things. So we can fail to prepare the input, which is what we saw earlier. If for some reason it hasn't written to EFS after multiple seconds, we'll get an exception here. If it times out, we'll get a timeout exception here with the status set to timeout. That gives you then that mysterious error message that everyone hates. If it's got excessive input output, it will get killed for that. Sometimes it will get exception for a reason we don't know, in which case you get this unknown error. But presuming everything goes fine, we then want to write stuff back, and we write back the output. And the output just involves us going through each of those output file paths that we saw earlier, for the representers where it was the .text, the .json. For the test run, it was just results.json. We read all of those files out, we put them together, we create a hash, and then, presuming everything works well, we end up calling back to the worker, which calls back to send the status and the output back to the tooling orchestrator. We saw the tooling orchestrator earlier. I'll show you. I've got it over here somewhere. So the other thing a tooling orchestrator can get is the job ID that comes back that says this is fine, this is happy. And if I just bring this up. This does two things. It sorts the job status out in Redis, and then it also informs our SPI, which I'll talk about in a second. Let me just see if anyone's got questions first. Why copy meta in? We copy meta in because there are files that maintainers can put in meta that are important for them. So, for example, there is the exemplar file, which you get for different languages. And a representer might want to check whether the student submission is exactly the same as the exemplar. And if it is, leave them a nice message. But chats can also use this for anything they want. So I can't think of any examples, but maintainers in the chat can maybe tell you. But if different exercises need certain flag setting or certain properties that are only relevant to an analyzer or a test runner, that's a place that maintainers can put stuff. So meta as a directory has like 2 or 3 compulsory files, but it also has like unlimited other files that maintainers can put in if they want. So we pass meta just so if a maintainer wants to use any files, that's an easy way that they can do so. Cool. So going all the way back to the website, we have an API, which is what is public and what everyone uses, but we also have a SPI, which is the S stands for secure. And the only things that can access this SPI are other internal services. It's not accessible over the web. There's not a route to it. And so various things access this. So ChatGPT responses can access it. Our tooling thing can access it. The new OG image stuff that we've added, which isn't in here yet, but can access it. And so this basically is able just to ping back to this special endpoint and say, I'm processing a tooling job. And then one of a few things happen. It's depending on what job it is. But let's look at a test run job. So a test run job, firstly, we create a test run in the database. So this does a couple of things. One, it obviously creates the tooling job ID. It also creates an ops status, which says whether we succeeded at an ops level. So did we time out? Did we have too much output, something else, or was it 200? And it takes that raw results JSON and puts that in. So if we look at my last submission and look at the test run, you can see that this is exactly what you've got. So you've got a tooling job ID that's come back. You've got the ops status. You've got these raw results. So this is the JSON file that's just been saved in to SQL as JSON. And we pull a couple of other bits out as well. So when the submission is created, it's created with a couple of other things. So it's created with we extract the version, we extract the message, we extract the output, and we materialize those on here because we might need to look them up without and do searches on them and things. We also change the op status if for some reason we don't have a status in raw results. So if this is missing, this line, which sometimes happens because of bad bits of tooling, then that changes this to be a 400 basically. And we also set the git char, and we also set the git important files hash, which is this thing I talked about earlier. So we firstly create this, and then depending on what's happened, we have lots of different things we have to deal with. So do they pass? Does it fail? All has lots of different side effects. So we deal with those side effects, and I'll show you that. But then we broadcast, and broadcast is just sending a message via the WebSocket that says this is the test result. So that's the thing that then means back in the editor all the way through, you get the results out. So we have these different statuses, as you can see in here. This was the broadcast bit. Fundamentally, we do two things. We update the status of the submission. So we update whether that submission has passed or failed. And then we also update the status of the solution. And we only update the status of the solution if it's not. This is where it gets really complicated, as you can see. We only update the status of the solution if we're running this for the whole solution rather than just the submission. So if you're updating, if we're running just a random check, so say what I talked about earlier, where a new commit is pushed to a repo and we're retesting everyone's solutions, we don't then want to change the original status of that solution. So we don't do that. We only change the submission status in that situation, not the solution status. So, but the reason we call this method anyway, but what happens under the hood here, and this, I don't know if I'm going to get too complicated here because it is really complicated. So this was the thing where Eric and I spent a load of work reworking a load of this, and then had one last 5% to do, and then forgot what the 5% was, and then had to leave the PI open for 2 months until we remembered. And it took us a whole 8-hour day of trying to. It took me a whole 8-hour day of trying to work through what it was that was missing, which is a lesson to always leave notes for yourself. But yeah, so there's a whole load of stuff in here. I'm not going to go in it. It's too complicated and not relevant. But basically, we end up setting whether the solution is passing the latest tests, as well as whether it's passing as well as whether it's passing the test that the student is running. So depending on whether the student is hitting run tests or whether the infrastructure is running the tests in the background, takes us down two quite different code paths in all of this. But actually, how we do all of that is just by looking at this get important files hash, and whether the solution's get important files hash matches the get important files hash of that test run. So the hash of that of the files in Git for that exercise is the sort of magic key that glues all of this together. And you can see that even by the fact that when I call test run, so if I'm just calling this line of code down here, if you can see that, make it a bit bigger. So I'm getting myself a solution, getting my last submission, and then I'm just calling test run. So I'm just saying to the database, give me that test run. The actual SQL that's generated for that isn't looking up by a foreign key or something. It's looking up by, well, it is, but the key is the get important files hash of the test runs on the submission versus the get important files hash of that submission. And in fact, you can see, this might be a bad example because it's probably quite new, but if I do, yeah, let me just do, So if I get an iteration instead of a submission, okay, this is not going to be a good example. I've got way too much test data on my account to do this with. Okay, yeah, that's good. So if we map if we do that. So this, let's just recap what I've done here. So I've got a solution, and this is my solution for Ruby for Tufa. Then I've got my iterations, and I've got the last iteration I did for that. And then I've looked at the submission for that. So you remember I said that at the very beginning, iteration is a save point effectively. It's what shows up in your iterations UI. But it's effectively just a wrapper around one of the bazillions of submissions that you might submit. And if you submit via the CLI, well, we just make one submission and one iteration. So it is like one-to-one. But if you submit via the editor, every time you're hitting tests, you're creating a submission. But when you submit it successfully, that's when you create and link an iteration in. So this is getting the iteration, my last iteration of my Tufa, getting my submission for that, but then looking at all the test runs. And you can see that since July 22, there's been various times the tests have run on this when this exercise has been updated. And you can see these are the timestamps, and these are the git important files hashes. And you can also see there's duplication here. It's happened twice for each of these things, which was, I saw this a lot. I think it was a bug. It could also just be us writing lots of data, but I've guarded against that, so that won't happen in future now. But yeah, you can see that in the background, even though you're not touching this, your tests are being rerun lots of times. But now what we do, and when we call, if I just call .test run on this, so when I'm actually saying what are the tests for this submission, what it's actually doing is getting me is looking at what the git important files hash is, which is the 7131, and then it's saying, okay, well, my actual one is this, which is effectively the most latest. So it's effectively been able to automatically update, and now it just knows that the latest test run, the test run for the latest git important files hash, is the one that's relevant to me. But if for some reason this had failed on the last one, then it wouldn't consider that to be linked to it. That would just be a failed head test run. So it's really complicated, and I'm sort of sweeping massive broad strokes over a whole load of complication here. And this same thing is happening for representers and analyzers with different constraints and different things. So that's sort of like my big high-level overview of everything. I'm going to pause, drink some more coffee. I need some water because my throat is going sore. Do people have any questions? Is there anything I've glossed over? Is there anything you were hoping I would talk about that I've not talked about? I'd love to know. I'm happy to dig into things. Are there any bits that you would love me to do future deep dive sessions on? Is this just totally boring and uninteresting to you? Give me some feedback and some questions, so I know whether you want me to talk anymore. Good question. Would Sidekick not be appropriate for posting jobs off Redis? Yeah, I did consider Sidekick. Sidekick has the downside to Sidekick is it's opinionated about the order of jobs and about retries, and it's quite hard to sort of manually fudge things. There's other things. So one of the things I've not talked about yet is the background queue. So we have a background queue. I don't think there's anything in it right now. But when we're running all these tests in the background for these head test runs and stuff, that's all of those jobs are queued in Redis on a background queue. They're not queued on the primary queue. If they were queued in the primary queue, nobody's editor test runs would work until that was finished. So if we have a little look, I'll do it in GitHub. Oh, I'll tell you what, this is very dark, very bright. Now it's getting dark. So if we have a little look in here, the background queue is quite a simple way of doing stuff. But basically what we do is we check how many things are in the normal queue. Let me turn this brightness down here a little bit. Oh no, that's great. That turns the brightness down on my laptop screen, but not on this screen. So we check how many items are in the normal queue, and if there's nothing in the normal queue, then we push. No, sorry, we have a max queue length, so we have a queue length of, I think it's 5 now, 4. Okay, so we see how many things are in there. So if there's 3 things in the normal queue, that leaves a count of 1. And so basically we say we should only have one. We should move one thing from the background queue in. So we're effectively, once we've got not much load on the queue, where I'm determining load as like having 4 or less things in the queue, or less than 4 things in the queue. At that point, we start backfilling the queue with things from the background queue. So we've got primary queue. Once it gets down to like 2 things in it, we backfill another 2 things off the background queue. And so in doing it that way, we're never impacting performance of the main queue, but we are working through the background queue. So there's behaviors like that which Sidekick just wouldn't allow for. That is why I chose to do it like this. Sidekick would have been, there's a lot of different alternatives. Like as I said, we started with like 0MQ for a lot of this, and actually just like having things queued throughout the whole thing. And yeah, there's lots of things. I also felt like Sidekick was I would want to run a separate Sidekick up, and I felt it was a bit heavy with active job and everything else to make that work. But yeah, Sidekick would have been a perfectly reasonable choice if I could have found some way to come around certain constraints on this. I've also just like evolved this a lot and iterated it a lot, and I've quite liked just being able just to do whatever I wanted with the code rather than having constraints. But at some point in the future, maybe I would reconsider it Sidekick, because, you know, as you can see here, we use Sidekick a lot. We rely on it. We've got lots of different queues and all sorts of things here. We use it for recurring jobs as well. There's a lot of stuff here you'll see, like syncing pull requests, reputation, lots of rechecking insiders, all sorts of things, sweeping things, all of these jobs in Sidekick that are happening sporadically as well, and on a sort of cron. So there's lots of stuff we do use Sidekick for. So yeah, it's a good question. Do you run tests after changes for all students? Yeah, we run stuff for every submission. We consider everyone to be active. And that's something we could do, which is like reduce that. So see a couple of jobs going here. So yeah, we could reduce it so we mark students as active, and once they become active, we maybe rerun some of their backlog or things like that. Because it runs in a background queue, it sort of doesn't matter too much. But yeah, that's a nice idea. We could also offer things like that as like a premium or insiders thing as well, so that you automatically get your things run to see if they can be updated as a premium feature. You know, as it costs us money and resource to do that, I think that would be a reasonable thing to do. The downside for normal users, in inverted commas, then, is they would just get the banner a lot more, whereas insiders and premium users won't get the banner. So that's maybe something we could consider, just to save ourselves some cost and resource. That's a good question. So the question is, would it save Exercism money if the CLI we use for the majority of submissions? Not really. So let's just in fact, let's look at our bill. So this is our billing dashboard. So if we dig into our cost explorer, costs in millions of pounds. So if we dig into this and look at EC2 instances and look at T3 mediums, is this okay, let's not look at T3 medium second. So it costs us roughly $400 a month. I'd say the most that we like, if we didn't have test runners, the most we could reduce it probably would be by like we could probably halve it, so it'd probably go down to 200. So it would save us $2,000 a year, which is not insignificant money, but it's that £200 out of like that's $200 out of like a $5,000 bill is sort of a small bit of stuff really. What would really help is if people stopped trying to DDoS us, and if people stopped like deciding we're really fun to test their hacking skills on and other things, because like other things like our ESC bills are more. It's like 700 a month, 1,000 a month, and a lot of that is just because we get these massive spikes in load. Our biggest thing now is RDS. This is relatively expensive. Considering this is just one database that's running away, I always think it's a bit expensive. I'm about to upgrade us, and I'll probably live stream it as well. I'm going to do it with a friend of mine, Doug, who some of you might know. But we're going to update to the latest version of Aura. So at the moment we're on serverless version 1, and we're going to update to serverless version 2. That's going to do... always scares me so much when I see DB instances 0 there. That's going to do two things for us. One, the auto scaling's a lot better, so it will auto scale more nicely for us, and you can also auto scale to smaller smaller increments. But also it's the latest version of MySQL, and one of the I think I'm blurry on that. One of the pain points for us at the moment is that we can't add descending indexes. So at the moment, if you have descending indexes, MySQL just can't use the index. So it's really slow. So there was an example. An example of ordering the site updates that appear on the dashboard. So I was like, where are we going? I was playing with this yesterday. So these updates like here. So at the moment, these updates take 400 milliseconds to pull from the database. And that's simply because we order them by when they were published in descending order. And because of that, MySQL can't use an index for ordering. MySQL 8 would return this data in like 1 millisecond. But MySQL, whatever the previous version was, because it wasn't 7, takes like 400 milliseconds because it can't use descending indexes. So that's going to be a massive performance gain in lots of weird places. Like ordering by reputation descending. There's so many things like that that we that will just be nice. So one of the things we're going to do is that anyway, which will save us a bit of cost, but it will also increase the granularity of the capacity unit stuff that you get with AOR. But it does involve like 5 minutes of downtime and a bit of stress. So we'll live stream it, the stress will be fun to share. But yeah, and Doug's going to help me with that. But he just had his second kid last week. So congratulations, Doug. And I'll give you an extra few days before I make you do this. More questions. I did the rough costs without seeing that. yeah, do you have any other questions about the costs? I'm happy to show you a breakdown of any costs. You said that if you, Bobby says, if you run all of the tests, rewrote all the test runners in JavaScript, could you push the computation to the client? Yeah. So, yeah, I mean, WebAssembly is the answer really to that. If they were all WebAssembly, then yeah, all of the cost could go to the client for that. But again, it's only like $200. And you're asking people to download heavy WebAssembly stuff, which makes Exercism less accessible for people. So the downsides probably outweigh the upsides. The big upsides of that would be you wouldn't have any like infrastructure pain. Like you wouldn't be in a queue. You wouldn't. There's lots of things like that wouldn't affect you. So yeah, where this would really get cheaper is if this could run on AWS Lambda, so that we only like had to run the servers when we were actually running stuff. So if we were just running, if it only ran that Lambda when somebody was actually running their tests, so you're only paying for used CPU, but we just can't do it because they reuse Lambdas. So yeah, that's frustrating. The other thing that would reduce costs would be if we were able to use spot instances for EC2, which I'm almost certain we could do, but I just don't know enough about it and I haven't invested the time into it. Again, just because it's saving like $200. The big thing, I mean, the thing with Exercism's costs, servers are, now we've sadly had to let Loretta and Jonathan go. Servers are a quarter of our costs. Our total costs are like me, Eric, Aaron, and servers. And paying, paying 3 salaries is more. And the reality is it takes a lot of my week, keeping wheels spinning, keeping things moving. It takes a lot of Eric's week, dealing with pull requests, dealing with other stuff. I mean, this week's been really nice. It's the first week in a year I've mainly coded for the whole week. And I feel like I've got loads done. We've got trophies half built. I've made loads of performance improvements. I've merged tons of PRs. I do feel like now I'm able to code again, then we're going to move a lot faster. And I think, Eric is more excited as well to have me coding with him. The downside is we have no revenue coming in as a result of that. Losing Loretta has meant that the revenue pipeline we were building has gone. So, there's just a big question of it's not really the servers, it's everything else around that's the cost of Exercism. But that's a question that I'm going to kick 12 months down the line now. You might have been on the last community call where I talked a bit about this. I'm going to put an insider's video about it. But basically, we're just going to have fun, try and make Exercism as great as it can. And if we run out of money in 12 months, then, premium and insiders, premium and donations rather, pretty much cover server costs now. So even if we had to, like, me, Eric, and Aaron stop working on Exercism, the servers would still run at this point. So yeah, but we're going to see what happens. Our plan is to put some courses together. I'm going to be putting a course together for Go and other things like video upgrades to the courses. And I'm hoping that if we can get enough of those, then that will, even if it just paid like me to do a couple of days a week, that might be enough just to keep things moving forward. We'll see. But we've got 12 months to just build some amazing stuff, have some fun, and we're going to see where we get to in 12 months. But I appreciate the questions and the care about our costs. Yeah. See any more questions? Yeah. There's the running, like pushing CLI stuff as well could work. But I think from a cost perspective, it's not the cost of like writing, like the cost of fixing the CLI, working on that, doing it, adding that functionality to the website probably costs more in like salary costs than it does in server costs over a year. Like, so the trade-off's probably just not that worth it. Yeah. Cool. Right. Well, my voice is going. That's been 2 hours, so I think I'm going to stop there. I'll answer this one last question first. Yeah, so some tracks have got syllabuses and what we call learning mode, and some tracks don't. It's a lot of work to build a syllabus. My hope would be eventually every track has a syllabus, but it needs volunteers to volunteer to do that. And we do have loads of wonderful volunteers who are doing that. Meatball, for example, has done great work recently in quickly sort of just building out like the fundamental bits of syllabuses. And then we've got loads of other maintainers who have, really gone deep on their syllabuses. You mentioned, Go and JavaScript there. Other languages, Elixir, Python, building out lots of deep, detailed syllabuses. So the hope is that we can start getting foundational syllabuses everywhere, and then over time we can really improve those. But all of that's down to volunteers. So yeah, we need people who are willing to give their time to that. But there's other work we're doing. Francisca talked about it a bit on the last call about building sort of generic introductions to concepts that are useful as well, that I hope maybe reduce some of the burden of writing the concept introductions a little bit. They are very language specific, but maybe they sort of take away some of the generic stuff. And I do feel like once we've got syllabuses in 20 languages, it makes it a lot easier to do it for the next 20, because you can pick and sort of jigsaw together from other places a little bit more. I'm not playing down the amount of work it is, because it is a lot of work. But yeah, that's my thinking on that. It's just a maintainer thing. Vang on C++. There's loads of people that have been working on this really hard. I really call Meatball out because he's done it on about 7 different tracks. A bit like Glenn's done as well recently. Like Glenn at the end of last year, just sort of blitzed out syllabus in a few places, or blitzed out tracks at least in a few places. Meatball's doing the same with syllabus across the place. But yeah, there's been lots of people recently who have been doing an amazing job of that, and massively grateful to everyone. I always dislike naming anyone because I always exclude other people when I do that. But yeah, Vang's done I never know how to say that. Vang has done a great job on C++ recently as well. Cool. All right, I'm going to leave it there. Thank you everyone for watching. Thanks to everyone that's been in the comments as well. If you'd like me to do more deep dives like this on anything, please just shout on Discord. Really happy to do these. It's fun for me to talk people through all the code we've written. Just let me know which areas are interesting. And we'll go back to probably a normal community call in the next week or two. I want to talk a bit about track trophies. Thanks to everyone that was posting in that track trophies forum post, by the way. I know I sort of cut it off a little bit. I didn't really mean to be spoil sport. I just didn't want everyone getting too excited and then us not doing that. But I think we are going to have, as I said, 6 track generic trophies and 6 track specific trophies. I've written the code for that. So you'll be able to choose which 6 track specific trophies you have. But as I said on there, I don't want to make 6 different ones for every single track. Otherwise, we're going to be in pain. But thanks so much. Really appreciate everyone being there. I hope you all have a really nice weekend. Take care.